I was recently watching a YouTube channel where they were discussing the effect of guitar cables on the sound of the guitar. So I decided to have a go with my pickup analyzer to see what effect the cables have. Obviously having the pickup inside the guitar gives you a different result to when you're testing the pickup on its own, because of the capacitor in the guitar and the resistors, which are the potentiometers. But it's interesting to see, you can certainly define differences between different cables on that normal frequency response or characteristic that you'd see from the guitar. The normal version I test with a patch cable, because the patch cable hasn't got virtually no effect on it. It's too short to have any capacitive effect. Basically cables are capacitors, so I'm expecting to see a capacitive effect on the results. So I've got a whole range of cables. This is on medium quality, I guess. 5 meters long. Another one which is, I don't know, also medium quality, I guess. 5 meters long. I've got a good quality Fender cable, 3 meters long. A good quality Fender cable as well, which came with a guitar that I bought, I think. Yeah, the Stratocaster I bought 20 years ago. So it's quite an old cable that's been used quite a lot, also 3 meters long. And this is then an Ernie Ball cable, 3 meters long. The guitars I'm going to be testing on are Gibson ES335 and a Fender Precision Bass. Yeah, so this is a reminder of what I'm going to use to carry out the tests. This Guitar Pickup Analyser I've been developing for the last 6 months. What it does is it measures the frequency response of a pickup between 20 Hz and 20 kHz. It measures the resonant frequency. The resonant frequency is then the point at which the pickup reacts most. The inductance then is the normal measured value of a coil, which is what a pickup is. The DC resistance is, is an indicator. It's not really relevant because its value is only relevant at 0 Hz, so there's no frequency change. So, but it is an indicator of sort of amount of windings on the pickup. The gauge of the wire as well. The Gauss value then, which I can also measure, is measures the pickup strength. So there's a separate test for carrying out, but there's a separate sensor for measuring the pickup magnet strength. The whole point of this is basically the response to frequencies. So I did a bit of research into which frequencies are relevant for the guitar. And for the bass, start at the lowest end, it's basically starts around 30 Hz, which goes up then to 440 Hz. Guitar starts typically at 82 Hz, up to 1.3 kHz. As a point of interest, the 20th fret on a guitar on the top E string is 2.6 kHz. And typically, the frequency response of a pickup starts at maybe 4 kHz, which is higher than all of the notes we're playing on the guitar, which was a bit strange. So initially I thought maybe I was doing something wrong. I mean, if you're looking at around 4 kHz, that's at the end almost of a piano, yeah. So the piano operates at 3.9, 4 kHz. It stops. So what I didn't quite possibly take into account was that the harmonics that occur when you play a guitar string at much higher frequencies. So what the pickup is responding, giving it its voice, really is its response to the higher frequencies, which are not the frequencies that you're playing almost. So the character of the pickup is certainly influenced by these higher frequencies that aren't the frequencies of the strings that you're playing. Yes, so the first test I did was connecting up my pickup analyzer directly to the guitar through a patch cable. So a patch cable is very short, which means that it has a very limited effect on the signal, on what you're measuring. So basically the graph that you can see on the screen above patch cable is the bass response of that guitar on the treble pickup. If you add a Fender 3-meter cable to it, then as you can see, there's a massive effect on the signal. What this graph is showing you on the left hand side of the graph is 20 Hertz, so the value it gives out at 20 Hertz, and the right hand side is the value it gives out at 20 kilohertz. So as you can see in the patch cable, you've got sort of valid values from 20 Hertz up to 20 kilohertz. When you put a 3-meter cable onto the guitar, it's created a bit of a spike at the highest value, so the resonant frequency looks even slightly higher. But importantly, you can see that the higher frequencies above the resonant frequencies are tailing off a lot quicker than using the patch cable. So this is now an Ernie Ball 3-meter cable and a Duesenberg 6-meter cable. So Duesenberg is a fairly good quality cable. We're at 6 meters long, so that will have an effect. And the Ernie Ball is a 3-meter cable. I mean, theoretically shouldn't have that problem, but maybe it's because the cable's old or faulty, or not 100% what it used to be. There's a possibility. So I mean, we've got almost an identical response to the 6-meter Duesenberg cable. And this is where it gets really funny now. It's Harley Benton vintage cable, some vintage tweed cable, which is 6 meters long, had an enormous effect on the signal, to the point where you certainly wouldn't want to use that cable, that 6-meter cable, as your primary cable on the guitar. It wouldn't make so much of a difference if it was on the secondary side of your effects pedal, maybe, but on the primary side it's got a massive influence over the frequency response of your guitar. I mean, you can hear that, definitely. It sounds a bit less responsive, the guitar, I would say, yeah. So what you can see here is the results page for the different cables. The inductance, also started off with the DC resistance. DC resistance doesn't change hardly at all, so it means that the resistance of the cable has virtually no effect. So the resistance is essentially zero of the cable, all of the cables. The inductance, the effect on the inductance measurement is fairly relevant, but I would say between 5.4 Henrys and 6 Henrys, you've got pickups with those sort of inductances, and you can have good ones with 6 Henrys and 5.4 Henrys, so that's not so much it's not so relevant. What is relevant though is the frequency response. As you can see with the patch cables, so the bass frequency response is 3.3 kilohertz. And if you take then the worst case, you're losing over 1 kilohertz of frequency response at the resonant frequency. So you're losing a lot of high end. And at 20 kilohertz, which is where it tails off, obviously it's not that relevant, 20 kilohertz, but it means that the signal is, prior to that, obviously disappearing, and there's a massive change there, massive, between 8.1 decibels, that's a minus 8.1, the bass value reducing down to 22 decibels, that's a minus 22 decibels on the Harley Benton cable. So I mean, it is quite clear to see that what the cable is doing is it's acting as a low pass filter. So it's letting all the low frequencies through, and the high frequencies are being erased. That's a simple way to describe it. Yeah. We go over to the Fender, the P bass now. As you can see with the patch cable, this sort of bass response, I mentioned in my previous video, there seems to be interaction between the two pickups. There's two pickups basically that act as humbuckers, and at some point in the middle there you can see it sort of flattens off, and I think they're reacting with each other a little bit, not in a bad way. It's all part of the character of the song. So and as you can see, we're talking about a bass guitar now. Yeah, so it's probably not going to have so much effect with a bass guitar, but again, it'll affect the harmonics and general sound. So the 3-meter Fender cable is having a definite effect on the high end frequencies, which is obviously getting worse as you go up there. So the Ernie Ball cable, which seems to have a worse frequency response than the Fender cable, and the 6-meter Duesenberg, is having an effect, chopping away all the higher frequencies. And the Harley Benton one is removing the higher frequencies completely, basically. Yeah, so I would have thought that with that cable you'd certainly get a kind of muffled sound from the guitar. And again, then you can see the effect here, the 6.5 Henrys to 7.2 Henrys. The inductance, the DC resistance, again, is not changing. Resonant frequency is halving. So, I mean, that is quite a remarkable effect. So its response is 2 kilohertz. Yeah, but it's not affecting the actual amplitude of the signal. So the amplitudes are the same, but it's just at a much lower frequency. Yeah, 20 hertz is not much effect, and at 20 kilohertz again you're seeing this massive degradation in the signal capability. Again, in conclusion, a cable is a capacitor. It's as simple as that. And yeah, a capacitor will pass AC signals to ground, and that's exactly what's happening. And the least capacitance, the less effect it has, and the more capacitance, which obviously with the cable length has got a massive effect on that. Yeah, I mean, you could say it's worse, I think, but I think it was quite clear to see that where you're losing, we're down to minus 17 decibels on the high end, that you're definitely losing enough signal there that you'll definitely notice that, yeah. Yeah, so I mean, in essence, the Fender 3-meter cable is, which I guess I've noticed, I've tended to use that cable on the front end, so I've sort of noticed that it has a cleaner sound, I would say, yeah. And I've got the 2 Fender cables. I've got another one which is much older and has exactly the same response characteristics as this Fender one that I actually have documented here.